He was working with Jeremy, and he has particular interests in kernels and kernel design. And I think he even gave a talk to the research group. Was it shortly after the talk to the research group that I suggested the summer school? I think it may have been. So he gave a talk to the research group about kernel design from the perspective of reproducing kernel Hilbert spaces. After which I said, you know, you think about this for a while, we should be doing a summer school where we talk all about Gaussian processes, and you should do the talk on kernel design, and, I don't think he knew this maybe at the time, you should also do an enormous amount of organisation to pull the whole thing together. So he agreed, perhaps not knowing about the organisation. But I think before he starts, I think just a quick sort of thanks to Nicolas for a lot of work on the organisation, getting funding together for the food, working closely with the rest of the group in getting the labs together, emailing you all, registration. It's been a lot of work for him, and a lot of probable stress, which he kept all the way from me, which is ideal. And then also he's going to give his talk on kernel design. So over to Nicolas.
Thank you very much, Neil. So after the two great talks we had this morning, you may wonder why this guy talking. That's because I made the list of the guy talking, so I put my name on the list. So here I am. So I'm going to talk about kernel design, not from the reproducing kernel Hilbert space point of view. I try to keep things rather easy to understand for a large audience, because there are some people that are new to the subject, some others that are experts, so I will try to juggle between both. So we've seen during the introduction lecture this morning, during the lab sessions, that a GP depends on two functions. The first one is its mean. So most of the time for now we assume that the mean was equal to 0. But you've seen that after conditioning the GP, then the mean was not, the posterior mean was not equal to 0 anymore. So there's the mean and there's the covariance, or the kernel, or it has many names again, but I will talk about covariance, kernel, in a way that the word means the same to me. So it's on this object that I will focus during my talk. So the charge of the kernel, you've seen that during the lab, hopefully. It has a great importance in GP regression. So we have here the expression of the posterior mean, and here the expression of the posterior variance. And as you can see in these equations, the kernel appears everywhere, because here K is a vector that contains some evaluations of the kernel. This is the covariance matrix that also depends on the kernel. So it really is a key object when you're doing some Gaussian process regression or Gaussian process models in general. So since it appears everywhere, it has a great influence on the model. So that's the same data set and two different kernel. You may notice something on this slide. I exchanged the two titles. So this one is the Gaussian kernel, or RDF, or squared exponential, and again, the one on the right is with an exponential kernel. So the charge of the kernel has to reflect the prior belief we have on the function to approximate. So we can't say like that one model is better than the other. For example, it would be not a good thing to say, oh, I do prefer this model because the confidence interval are narrower. No, it really depends on the function you want to approximate. If the function you approximate is actually something that goes like that, this model is very bad, and the model you really want is the one on the right. So that's one key point, that the kernel has to reflect the prior belief you have on the function you model. So here's the outline for the talk. So first introduction, then what's a kernel with some definitions, the link between kernel and positive measures, making new from old, so how can we transform existing covariance functions into a new one, and then I'll finish with a very short conclusion. So first we call some definitions. So we already had some definitions for GP this morning, and here is, I would say, a new one. I don't think you used this one this morning. So first thing, a Gaussian vector is, so a d-dimensional random vector is said to be Gaussian if whatever linear combination you make of it, you end up with a Gaussian. And the Gaussian process is related to a Gaussian vector in the sense that whatever point you choose here in the input space, the vector you create is a Gaussian vector. So a better way to see this definition is to make some little pictures. So here is a random process Z. So I can take some arbitrary points in the input space here and then evaluate the process Z. So I obtain a cloud. So here I represented the first x1 versus x2, so for these two variables. So the process Z is Gaussian if and only if the points over there, the cloud, is distributed as a multivariate normal. And what is a multivariate normal distribution? It means that if you take a subspace T and if you project onto this subspace, then you will end up with a new collection of points, and this is a multivariate Gaussian if and only if here you have a Gaussian distribution for the points you sample from their definition. So I recall here the definition of the kernel. So k of x, or maybe here k of xy is equal to the covariance between the process at the point evaluated at the point x and the process evaluated at the point y. So first example, if you calculate k of xx, it's this covariance. So this covariance between something and itself is a variance, so it has to be positive. Another property is that if you compute k of x, it's equal to this covariance. The covariance is symmetric, so you can flip both z of x and z of y, and you obtain in the end k of yx, so that means that k is symmetric. So this is two very basic results. We can obtain one that is much, much thinner, which is the following. So we introduce the random variable t, which is equal to a linear combination of the process evaluated at some arbitrary points xi, and we set n, ai, and xi to be arbitrary. So n is a real, n is natural, a is a real, and x is a point in the input space. So if we compute the variance of this guy, we obtain that, and we obtain this expression. So the variance of t is equal to that. So by definition of the variance, this has to be greater or equal than 0. So this is a key definition. The function that satisfy this inequality for all arbitrary n, a, and xi are called positive semi-definite functions. So this is true whatever the covariance you're looking at. Z does not necessarily is a GP here, but every kernel of a random process is a positive semi-definite function.
Am I right in thinking that that's just the mathematical representation for that?
Yeah, exactly. Yeah.
Projection onto.
Yeah, you can come back to these images, and then you understand this variable very well. It's just the one we had on previously on the right. So we've just seen in the previous slide that if k is a covariance, then k is a positive semi-definite function. It's vice versa, and there's a theorem called the love theorem that gives the equivalence between both. So the issue is that to show that a function is positive definite is often intractable. So if we recall the definition, we have to see that. So it's the size of the sum Rn, which is arbitrary. The points here can be any real, and the xi are any points in the input space. So if you want to check that, most of the time it's impossible to go for a direct proof. So a common approach is to use well-known kernels. So we've seen some this morning. The white noise, we've been using it during the tutorials. The bias is just the kernel is equal to a constant, not also positive definite. The exponential kernel we've been talking about this morning. The Brownian kernel, Gaussian, square exponential, and so on and so on. The Mathean kernel, the same kernel. So there's a huge list if you start to dig into the literature, and you'll find many covariance functions. And you can make two big class of covariance functions. The one that are functions of x minus y, which are called stationary kernels, and the ones that are not. So for example here, they all are stationary kernels except the Brownian. So here's an example from the documentation of GPy with some representation of kernels. So the usual ones, some that are a bit more strange kernels for periodic functions, and you may find this one and this one a bit strange because they don't look symmetric. In the definition, a kernel had to be symmetric. Actually, they still are symmetric in the way we want them to be, because if you compute, so the Brownian kernel, we have k is equal to the minimum between x and y. So if we take 2 points here, I represent two functions. Here this is k of x dot, and this is k of y dot. And now if we evaluate k of x, y, so we take this function and we evaluate it in y, we have this value, and if we take k of yx, we end up here with this value. So it is indeed symmetric when you look at its two variables. Here you can flip both, but it does not have a symmetric shape over here. So now there's one slide on stationary kernels. So stationary kernels can be written as a function of the difference between x and y. So here's two property. So if this guy is n-time differentiable in 0, then it is n-time differentiable everywhere. So here's the example. Here its derivative exists in 0, but the derivative does not exist here. So this means that this cannot be a valid covariance function. And here it's kind of similar because it's continuous here, but it's discontinuous elsewhere. So these two functions, given this property, they can be positive definite functions. And the other property is that the maximum value of k evaluated at t is reached in t equals 0. So this means that a function that has this shape cannot be a stationary kernel. So I'm not going to make the link between kernels and positive measure. So we have an important theorem called Bochner theorem, which says that a stationary function k is positive definite if and only if the function seen as a function of just one variable t can be represented as the Fourier transform of a positive measure. So this result is very useful to prove the positive definiteness of stationary functions. So here's an example. So we take the step function that is centered around 0, and then we compute the Fourier transform, the inverse Fourier transform from this guy, and we obtain this function, the sinc function, sine t over t. And by using the theorem, since this is a positive measure, so we have 0 here and I guess 1 over there, by given Bochner theorem, then we know directly that this guy is positive definite, so you can use that as a valid covariance function in your models. Bochner theorem can be used to prove the positive definiteness of many usual stationary kernels. For example, the Gaussian is the Fourier transform of itself, so it is positive definite. The white noise kernel is the Fourier transform of the constant function. The constant function is a positive measure, so this is positive definite. and the other way around, if you take the Fourier transform, the inverse Fourier transform from the constant function, you end up with the white noise kernel, which is PSD. So here's another example on how to create kernel using this property. So this is from Andrew Wilson, who came here for a seminar a few months ago. So I took this kernel from one of his papers in ICML. So the Fourier transform of a symmetric non-centered Gaussian is like that. So I take a Gaussian here, over there, and then I make it symmetric. Why do I make it symmetric? And why does my function here is symmetric around 0? That's because when I take the inverse Fourier transform of this measure, I don't want my result to have an imaginary part. So here I only consider a symmetric function, so I'm sure that I will end up with a real function in the end. So if I take the Fourier transform of this sum of two Gaussian, I obtain this kind of shape, which is the product between a cosine and an squared exponential kernel. So the cos RBF, I think it was in the lab, you've been using it. So provided that we can generalize it by considering here a more complex structure where we sum many Gaussians in the measure space, so we will try to approximate the spectrum of the function we want. So someone asked a question on how to build a kernel in a, say, less parametric way. It's still parametric because you're adding more parameters, but you're doing this parameterized estimation in the Fourier space. So yeah, instead of taking one, we will take a lot of Gaussians, so they will be parameterized by their mean and their band width. And this is the kind of measure we can end up. And if you take the inverse Fourier transform of this measure, which is positive, you end up with a positive definite function that you can use as a kernel. So for example, if I take this kernel and if I simulate some sample path, they have roughly periodical behavior, because you can see that the maximum are kind of regularly spaced over the input space, but it's not perfectly periodic because there's some kind of decay in this function.
Nicolas,
yeah.
Quick question. So in the Blockner's theorem,
yeah.
does mu need to be symmetric? About 0?
No, because I think this theorem is written for kernels over C. So it's more general, and here I'm just interested in kernels over R. So you don't need the function to be symmetric, but you will end up with a complex process in the end.
So if you want it to be, if you just want to work out R, you do need to have a symmetric
yes.
response.
Yes. So now we've seen that the definition of a kernel, that they correspond to positive definite function, that in the stationary case then we have Blockner theorem that allows to create new kernels or to check quite easily if a function is positive definite or not. But in the non-stationary case we don't have much results. So there's something that is quite common, which is called making new from old, where you take some kernels that you know they are positive definite, and then you look at the operations you can make from them to transform them, to tweak them, to somehow you torture a bit your kernel to make it something that is more interesting to the model you want to build. So this is the things we are going to talk about. So yeah, we've seen that it's difficult to prove directly the positive semi-definiteness of a function because of this for all n in the natural, for all x in the input space, and for all the ai in R. But however, we can make many operations on kernel that we know that they satisfy this condition, and we end up with new kernel. So I will talk about the following operations. The first one is multiplication by a scalar. The second one is the sum of kernel, the product of kernel. So you've seen that a bit during the lab. So I bet you will have many questions about these. And the multiplication by a function, the composition with a function, and I will end up talking about one point that I think is of great interest, which is the effect of a linear operator. So is there any question for now?
we summarize Faulkner's theorem again?
Yeah, I will not use it a lot anymore. So, yeah, I will start from this. So here you have a measure mu. From this measure, you can compute its inverse Fourier transform, which is given by this formula. So this will give you a function here. And if the measure you use here is positive, so here it's positive in the sense that it's greater than 0 everywhere. It's the usual sense of being positive for a function. So yeah, if this is positive, so this is very easy to check, then you will end up with a positive definite function over here. So yeah, that was the very basic example. You take a measure, you compute its Fourier transform, and you are sure that you have a proper kernel to work with.
So, but the mu does not have to satisfy any of the previous conditions of maximum 0 or...
No. Mu here is very general. It just has to be greater than 0 in every point. But that's fairly easy to check, for example, yeah. This one, that's straightforward. The Gaussian, for this example, you can see that a Gaussian is positive, we know it. And we end up with a much stronger result, which is that as a covariance is positive definite, which is much more complex to show without this theorem. Yeah? So, yeah. So we assume that in all this section I will use Ki and Zi. So it's just Ki is one kernel and Zi is the GP associated with this kernel. I will use most of the time centered process because it makes just the writing easier, but it's not more difficult to add, whatever you want. So if alpha is a positive real, then the multiplication of alpha by a kernel will give you another stuff that is a valid kernel. So this is straightforward to prove using the basic definition. Just I take, there should be a 1 here and there. So I want to prove that this is greater or equal than 0. I just can put my alpha out of the sums. And by definition, if there's the 1 here, by definition, K1 is a positive definite function. So this is true if alpha is positive. So that's a very basic. So here alpha somehow corresponds to the variance parameter that you've been estimating during the lab. So from a Gaussian process point of view, K is the covariance of the square root of alpha times Z1. So if you compute this covariance, the covariance is bilinear, so you can take the two square root of alpha in front of the covariance, and you end up with the kernel you want. So this is one proof to show that alpha K1 is positive definite. This is another proof because if we use Löw's theorem, we know that a covariance is a positive definite function. So here, this kernel corresponds to a covariance, so it is positive definite. The two are equivalent to show the positive definiteness. So now, the sum of kernels. Let f1 and f2 be two functions. So here I took two basic functions. If we compute the sum f equal f1 plus f2, there's two ways to compute this sum. The first one is to see f as a function defined over R. So we have f of x equal f1 of x plus f2 of x. So this is what we have for this dumb example. The other way to compute the sum is to compute the sum over the tensor space of the input space of the two functions. So we define here f, that is a bivariate functions, depending which is the sum of f1 and f2, but evaluated for two different inputs. So from two one-dimensional functions, by summing them, I can choose either to make a one-dimensional function or a two-dimensional functions. So it's...
Right.
Yeah.
I'm getting lost here. So 1 on x1 and x2 on your right-hand side.
Here they are just reals.
And how does that relate to the single x you've got?
Just here.
Define two functions of a common x.
Maybe I will show you a slide that is kind of later, but yeah, maybe this one explains it better. You have a function defined over one space, a function defined over another space, and then you multiply them, you add them together, and you obtain a function defined over the whole space. You can, or another way to write that down is to say, so we have f1 of x1 equal x1 times a constant function evaluated in x2 if you want. And then you have, it's just a way to say that this function f1, you can see it as a function of one variable, or you can see a hidden second variable saying that the function is constant is in the other direction. Is it all right? Yeah, so we can look at that for kernels. So here I'm looking at the sum of kernels defined over the same space. So this is the case we are looking at to start. So the kernel depends on two variables, but we evaluate the two kernels k1 and k2 for exactly the same variables as the variables of k. So the property is that this sum of kernel is a valid covariance structure. So the proof is quite straightforward. I think some of you got it during the lab because that was one of the questions in the lab sheet. We take this double sum. Here k is equal to the sum of k1 plus k2, so we write that down. And then we can split this sum into two sums, the first sum over k1 and the sum over k2. This guy is positive because k1 is positive definite. This guy is also positive because k2 is positive definite. So you end up with a result that is positive. So that shows that k is a valid covariance function. So you can sum covariance functions together when they are defined over the same space. So from a Gaussian process point of view, k is the kernel of the sum of z1 and z2. Now let's look at an example. So here I take a Gaussian kernel, and it's very tiny, but it's a very small exponential kernel. How cute is it? We end up with a new function that is positive definite. And this is the example of the sample path. So you can see that there's some kind of long-range effect that are given by the Gaussian, and some small variations over there that correspond to the exponential. So that's why I took a very, very small variance for the exponential kernel. Otherwise, we wouldn't have been able to see the effects, the smooth effect behind the function that is kind of noisy. So in practice, it's very useful to sum kernels. So that's a classic data set, which is the Mauna Loa observatory data set. So since 1968, they are recording every month the CO2 concentration in Hawaii in an observatory. And this data set is public. And you can see that the general trend. So given this data, we'll now try to predict over the next 20 years what's going on. So the first thing to do is to take a Gaussian kernel and to see what happens. So this is two models that I obtained with the Gaussian kernel. The results are terrible. That's some very, very bad predictions. So what's going on here? If we look at our functions, it has some kind of it involves two frequencies, the one for the very small variations over there, and the one for the large trends effects. So if we take a squared exponential kernel, it only has one length scale, and it's not able to represent these two components of the signal. So it will either converge towards the very, very small length scale we can see here, and then it says, okay, I have a large variance, but a very small length scale, and it comes back to the mean very, very quickly. And the other solution you can find is you can, when you optimize, you also can converge toward this kind of solution where the model picks the long-range effect, but it just ignores the small variations. So this is also a very bad model because the confidence interval here are clearly wrong. And here the confidence interval are kind of okay, but the mean predictor is very wrong. So just to take an idea, you have to model this data set that's very bad. So the question is, what happens if we sum both kernel? So we'll have the first one to take into account the small range, and the other one to take into account the large range effects. So we end up with a model that is much, much better, where we have the two components, the trend given by the long length scale and the small variations over there that are given by the small length scale. So this model is already much, much, much better, but as you can see, we have some periodicity here in our data, and that is not reflected by the model. So we'll make another kernel to approximate that, which is based on, oh yeah, and here there's roughly a quadratic effect. So I also added this, which we will see later is a positive definite function. So that's a kernel, some large length scale, some small length scale, and a term for the periodicity of the data. And this is the model we end up with. So just by summing kernels, we are specifying a prior that is much more suited to the data. And if you compare that, yeah, with the initial model we had, that's greatly, greatly improved. So now we've seen there was two ways to sum functions. I've been talking about defining kernel over the same space, and now we define kernels over different spaces. So here, k depends on x and y, and x has two components, x1 and x2, and y has two components, y1 and y2. So if we take this sum, this will also be a valid covariance structure, so it can be seen as either the same proof as before, or like that, where you define a bivariate process as the sum of two univariate processes. So what happens if we plug that into a GP? So we can simulate some sample path, and this is what we end up with. So if you can see, the function we obtain by simulating with this kernel are additive. So by choosing an additive kernel, we are specifying in our prior that we are working here with additive functions. So this kind of thing can be very useful for two reasons. The first one is to approximate a function that is additive, because then you give a lot of information in your prior by specifying my function is additive, so that will greatly improve the model. And the other one is for building model over high-dimensional input spaces. So now, yeah, I will discuss these 2 points with 2 examples. So here is a test function that is additive. So it depends on a function of x1 plus here a function of x2. We assume we have this test function that is represented over there, and a set of 20 observations. Now we use that to create a GP model. So here I use a usual Gaussian kernel in 2 dimensions, which is like that, where this is the usual norm over R. So the square of the norm is equal to the sum of the square of the xi minus yi. So we compare a usual kernel, so that's what we have for the main predictor. So as you can see, it's not an additive function. And we compare it with somehow the same one, but defined with an additive kernels. So here the root mean square error is equal to 1, and here the root mean square error is equal to 0.12, so there's a tenfold difference between the two RMSE. Yeah.
I was curious, what do you think would happen if you were to add those two kernels together and try and jointly fit them? Would it be able to identify, given that amount of data, that it's really additive?
Yeah, I think that if I sum both, and if I then estimate the parameter, my likelihood will turn off these components of the model. Yes, indeed. So, and if we compare the shapes of the two models, well, the test function really looks like the one based on an additive kernel. So it's straightforward to show that the mean predictor is additive. So if we write its expression, then we can expand with respect to the first sum, and we obtain a sum of two functions. So the first model M1 and M2, and these two guys can be interpreted as, they can also be interpreted as best predictor, because here K2, which is the covariance matrix given by the variation over X2, can be seen as some observation noise. So this is a best predictor, so this is the expectation of Y1 knowing Y1 plus Y2 equal Y. So these also are Gaussian process regression models. So what we have here is that M is additive, so the mean predictor shares the prior behavior. So if we look at the variance of our models, then, so here I've represented again the one with the RBF, and here the one with an additive RBF, and we can see that the two variances are very different, and they are much larger over here, because the model is very uncertain about what's going on in this region. But if you compare with this model, they are very small in this region, although there's no observations over there. So that may be a bit strange, but we can explain it. So if we consider, I take just a simpler training set. So I assume I know for 3 points the value, and I want to predict in X4. Then if you take an additive kernel, the process that is behind will be an additive process, and the value in X4 will be equal. So yeah, we compute the variance between the variance in X4 knowing the three observations, as Z is additive. The variance in X4, the value of the process in X4 is equal to the value in X2 plus the value in X3 minus the value in X1. And here we are looking at the conditional variance of a GP knowing every of the components, so this variance is equal to 0. So if we come back to our model here, then we can see that in this area there are some very small variances. That's because knowing the value here, here, and here, and knowing that your function is additive, then your model tells you, okay, you know your function very well here, because it's just equal to that plus that minus that. So there are some regions of the space like that with very small variances. So you can use this property to build some design of experiments. So here, for example, I want to approximate a function over 0,1 squared, and I put 1 point here like that distributed on every axis. The additive assumption I made in the beginning gives directly that I know my function everywhere on the grid. So this kind of model will scale very well with high-dimensional problems, as all the generalized additive models. So yeah, using an additive kernel is a way to build some generalized additive models with all the Gaussian process framework. So yeah, here we take into advantage the structure of the kernel to build a design of experiments that will give very small prediction variances. The thing is, having small prediction variances is not necessarily very good, because if the function is not additive here, we will never be able to tell. So an alternative is to change a little bit this design by moving some points. So for example, if I move this point over there, then I will still know the value everywhere on the grid, because moving the point here gives me the value there by using this triangle, and so on and so on. So you can modify. You don't necessarily have to build design that are focused on the axis, but yeah, you can have design that explore the space much better, but that will give you a very, very good coverage for the additive component of the function you want to approximate. So here for this 3 design, we would end up with exactly the same prediction variance for our model. So, yeah, the sum of kernel, I was talking about making models in high dimension. So here I will compare, we will see why they scale much better. That's because if you take a stationary kernel, it only depends on the distance between x and y. So it will only have a very local influence. So you can imagine that if the dimension is growing, and if you always have a very local influence, you will need more and more training points to cover the space. Whereas compared to this kind of design, here the number of points just have to increase linearly with the dimension. So we've been talking about the sum of kernel. What about the product of kernel? As previously, we can make product over the same space or over the tensor space. So here's the first example. So I take 2 kernels defined over the same space, I multiply them, and I end up with a new function that is still positive definite. So that's the kernel we've been talking about previously. So if I multiply a Gaussian kernel with a cosine, then I will end up with something like that, which is positive definite. So here's the sample path. I can also create, see the product of kernel as something to increase the dimension. So here K is defined as the product of 2 kernels over different spaces. This property tells us that this guy will be positive definite over the whole input space. So this can be used to obtain covariance structure in higher dimension. So for example, here I took the Gaussian kernel again. I multiply this one by this one, and I end up with this guy. And here you can recognize something that is roughly shaped like a Gaussian bell, and it is actually a Gaussian bell, because if you compute this product, you end up here with exactly the expression we had before for a b-dimensional Gaussian. Is there any question about that? No? Good. So that's from some sample path from a product of kernels, so that's just sample path from a usual 2-dimensional Gaussian kernel. So the thing here is that the Gaussian process cannot be seen as the product of 2 independent GPs with kernels K1 and K2, because if these 2 guys are Gaussian processes, then if you multiply them together, you do not end up with a Gaussian process anymore. So you end up with a non-Gaussian process that will have the same covariance, but it will not have the same higher moments. So we can also multiply a kernel by a function. So f can be any arbitrary function, and if you multiply k of xy by f of x, f of y, k1 of xy, that's a kernel over d1. So the proof is kind of straightforward, because we just have to rename this ai, fi as bi, and by definition, whatever the value here are, then K1 is positive definite, so this will be positive. So that can be seen as a generalization of the multiplication by a scalar, because in a scalar it's just f equal to a constant. And if you look at the product f of x, f of y, that is also a kernel in fact, because it is the covariance of alpha f of x, where alpha is Gaussian distributed. So I used it previously to put some quadratic components when we are looking at the Mauna Loa example. The first kernel I was using in my sum was sigma 0 x times y, no, x squared times y squared. So this is a quadratic kernel, and this is just a product of 2 functions. So So here's an example. So I take f of x equal 1 over x. So usual pattern kernel, then I multiply both, so f of x, f of y times this kernel, and this is what I obtained. So it's a kernel that is not stationary anymore, even though we start from a stationary one. And it has some huge variances around 0 because of the term 1 over x. And you can see that on the sample path where they kind of explode around 0, and then they have a smaller variance. So that can be seen as a rescaling of the output, where we take our usual material and we contract the space in this region and we expand the space in this region. So yeah, that can be seen as some rescaling of the output space. One of the properties is to compose a kernel with a function, so we also end up with a positive definite functions. So here the proof again is quite easy, because if we take this guy, we just plug the values of f here and we can rename that, and by definition of the positive definiteness, this is valid whatever the value here are, so this is positive. So what we can really see is that if you start from a positive definite function, you can modify it and then use the real definition, and it's often very easy to prove the positive definiteness given that k1 is positive definite. So here k corresponds to the covariance of z of x z1 evaluated at f evaluated at x. So you can wonder what happens if instead of f here you plug another GP, and then you end up with deep GPs. But here it's a much simpler case. So this corresponds to a rescaling of the input space, because what we have here, the f of x, will make a contraction of the space in this area and will expand the space in this area. So that's again, so we can make some very non-stationary kernels just by introducing this transformation of the input space. So I will finish my talk with the effect of a linear operator. So if L is a linear operator that commutes with the covariance, then we can show that this is a valid covariance function. The simple way to see that is that K is the kernel of your linear operator applied to the process. So the RKHS framework, so reproducing kernel in bed space, is very useful to work with this kind of property, but I don't want to go into the details now, but if you have some questions about that, I'll be very happy to answer them. And yeah, so we can do a lot of stuff with that. So for example, if we want to approximate a function that is symmetric with respect to 0.5, so the function is defined over 0, 1, we can look at two different linear operators. So the first one that just take f of x if x is greater than 0.5 and 1 minus x otherwise. So the first way, if you have a function f like that with 0, 1 is to center the function like that, you end up with something symmetric. The other one is to compute the average between both, and then you end up with something like that. Okay, so now using these two transformations, L1 and L2, we can define two new kernels and see what happens when we simulate the sample path from these kernels. So here we can see that the original regularity of our process is kind of broken, but we end up with sample path that satisfy the condition we wanted in the beginning, and with K2 it's kind of better because the regularity of our process is respected. So we can see that like that. So that's from the previous talk, so that's the notation for the reproducing kernel Hilbert space. But basically we have our function f, and here the subspace of symmetric functions, and there are many, many ways to project this function onto this subspace. And here is L1, here is L2, and the idea behind that is that there must be an optimal way to project f onto the subspace that will be given by the orthogonal projection onto this subspace. But we have no guarantee. Well, it's probably not this one, because this one breaks the regularity, and yeah, but there's one linear operator that will have more sense than the other one, the one that corresponds to an orthogonal projection. So, but that can be a difficult question to answer. I'm not sure about the answer here for symmetric functions, but I will illustrate that with another example, which is to compute, which is to approximate a function that satisfies this condition. So we want to approximate f, and we have an extra knowledge about f, which is that it's exactly a zero mean function, so the integral of f is equal to 0. So the question is, can we build a kernel that reflects these properties? So can we put this information we have in our prior? It's quite easy, as previously, to define an operator that will center the function f. So if you take f and if you subtract its integral, then you end up with a zero mean functions. So that's a projection onto the subspace of zero mean functions, and this projection is an orthogonal projection for L2. And what happens if we apply that to our process? So we define Z0 as the projection of L onto the subspace of zero mean functions. So Z0 is equal to Z minus its integral. So we can compute the covariance of Z0, blah, 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 and we end up with the kernel minus a univariate integral minus another univariate integral minus, oh, that should be a plus a bivariate integral in the end. So if we have a look at this kernel, yeah, we can use it to simulate some sample path. And if you compute the mean of this sample path, all the means will be exactly 0. So we are putting here the information we want in the prior just by specifying the appropriate kernel. And now we can also use this kernel to build some more models. So I compare here one model based on K, so the kernel we start with, and the one that corresponds to the centered version of our kernel. And the function I want to approximate here is the function in red. And this is what I obtain with the usual kernel. So it doesn't know that the function we approximate is actually zero mean, and most of the observations are below 0. So it will tend to stay in this region, and that gives a very poor fit of the function in this area. On the other hand, if you take a model that is based on the appropriate prior, the model knows that, and it knows, okay, I have to be exactly zero mean, so it has to go very high in this region to ensure the property that it's zero mean, and we end up with a model that is much, much, much better just because we took the appropriate kernel. So if we look at the little diagram we had, so we've seen that Z0 was the orthogonal projection of Z onto the subspace of zero mean functions. And the question is, are Z0 and Z minus Z0 independent? So in a sense, we are kind of checking if this orthogonality here also holds for the process, because the covariance can be seen as an inner product. and we end up with this expression, which is not equal to 0. So this diagram, which is in L2, we can make it again in the space where the inner product is defined by the covariance, so a space that has much more sense for the GP we are looking at than L2. And it turns out that this projection is not orthogonal because the two are correlated. So an alternative here is to change the way to center the function. So we can introduce a function here, g, that is a function with integral equal to 1. So this will also center the function f, but in a different manner. It can be shown that if you take this expression for g, then you obtain the covariance between z0, between z minus z0 and its projection equal to 0. So that's what we end up with. So in the space that has some sense for the Gaussian process, so yeah, where the covariance corresponds to an inner product, then you have this orthogonality. So when we were looking at previously along all the way to project a process onto the subspace of the Riemann function, this is the one we are looking at. This is the one that makes more sense. So yeah, we obtain finally the composition, the projection we were looking after. So here's 3 slides for the conclusion. So the main point is that the choice of the kernel has to be reflected by has to reflect the prior belief about the function to approximate. Kernels can and should be tailored to the problem at hand. So the good way to do that is to start from the usual kernel and then to modify, to torture it a little bit, to end up with something that is adapted to the model we want to create by adding more information in it, making new from old. So that's a way to avoid proving that a function is positive definite, is just to modify the usual ones. Here you've seen the multiplication, the sum, the multiplication by a function, and the composition, and there are other ones that I haven't discussed here. And the effect of a linear application. So if we have a linear application here should be operator. If you have a linear operator that transforms any function into a function that satisfies the desired property, then you can build the Gaussian process that is well suited for your problem at hand. Okay, do you have any questions? Yeah.
Since you demonstrated that this sort of Gaussian hill is a subset of this larger set of kernels that we define by using a function onto random variables, essentially.
Yes.
So can that, because we saw earlier that we can have these Gaussian processes essentially where we just replicate Gaussian processes again and again when we go higher than 2 dimensions. So can the same be said of these other kernels where we essentially have different functions associated with each random variable? When we go into higher dimensions, can we have a different function associated with each of them?
I'm not sure I understand the question.
So essentially what I'm saying is in a multivariate Gaussian process, a multivariate Gaussian distribution, what we are essentially doing is in each dimension we just associate a Gaussian process. But when we generalize it to all sorts of functions, what we do is that with each dimension we associate a function. Each function can be different.
Yes.
Is that all right?
Yeah. That's
so
all
that
right.
would mean that instead of all the covariances between each dimension being a hill, it would be some sort of 3-dimensional surface.
Yes.
So I was wondering if that leads to any sort of different applications than your general Gaussian processes do. Is there a niche subset of problems that can only be tractable by those sorts of function spaces other than just the multivariate Gaussian distributions?
I don't know, because the one, even if you build by, you take any functions and you build the kernel by multiplying that by Gaussian random variable, then you end up with a Gaussian process, whatever the function you started with. It will still be Gaussian distributed. So if you multiply, a cosine by a standard normal variable, then you will end up with a Gaussian process, and whatever the function you start with, you will never, somehow you have the deterministic part that is given by the function, and the probabilistic part that is given by your random variable. So whatever the construction you have in higher dimension, you still have the same framework, the framework of Gaussian process. There's no problem you can handle with this framework of summing functions. That's not different to getting usual GP. The only difference I can see is that one space will be finite dimensional and the other one will not. So one is some kind of classic linear regression where you have a finite number of basis functions, so like the cosine when I was talking before, and the other one you have an infinite number of basis functions, like the infinite number of parameters that Richard was talking during his talk this morning. Did that answer your question? Yeah, Jeremy.
Yeah, a couple of questions. I really like the Manuel-Lower example. When you had these different kernels, were you putting constraints to say that one has to have a smaller length scale than the other, or something like that? How was it distinguishing between?
No, the thing I was doing is I was doing my initialization at a sensible point, not too far from what I was expecting. Then the optimization went well and ended up with this result, but I was not specifying range for the parameters or this kind of thing.
So you can just start the ping off from different points and it's sensible and it just moves around and it all works.
Yeah, I'm not sure it would work all the time, but here, it worked.
That's a good question. So Jeremy's question was about in that, I don't know if you heard the example, the Manuel-Lower example where you've got the long-term trend and then the short-term trend. If you fit an example like that, and you fit by initializing the length scale of each kernel to be the same thing, it won't fit the example. Basically, they both confuse themselves and they try and fit the same length scale.
Yeah.
You have to initialize one of the length scales shorter than the other and hope that the length scales, because it's an example of sort of multiple optima, and you can get both kernels trapped in the same optima. Nothing to prevent them doing that.
Yeah, the only thing I did was to cheat a bit for these models, because they are incredibly unlikely, so the optimizer couldn't pick up that. So I specified here the values by hand. But once you take this one, then you're fine if you start the initialization somehow in the region you want. Yeah, because here you can see that you can exchange both. The likelihood space will be symmetric because your set of parameters you can exchange both and you end up with exactly the same model.
So just carry on that example. So, I mean, in this sort of, well, because normally Gaussian is used for data-driven model, but in these cases it's actually kind of required that you have some physical understanding of the system, say what you're trying to capture with different kernels. Is that true? If you don't have a physical understanding, say for example, I want this small trend to capture the seasonal change, and large trend to catch the technology evolution, then it would be quite difficult to actually make prediction for the future.
Yeah, so there are some methods where you can specify at the very beginning a very, very large number of kernels. So you start with an expression like that, but with something like 2 power 2 exponential the dimension of your space, something like that. So a very, very huge number of kernels in the sum, but you make some sparsity assumptions on these values over there. And then without yourself specifying any covariance, like here I gave it directly the right shape because I was looking at the data and say, okay, I want that to be in it. But if you start with a very, very large number of kernel, and if you make this sparsity assumption on the variances here, you will end up with a model that will select, that will do some automatic relevance determination, and that will select only the component you are interested in, but then it becomes quite heavy to optimize. But yeah, if you're interested, you can look at hierarchical kernel learning, or this kind of method, or some of all the methods that are based on lasso or lasso regression. This kind of stuff can be applied for GPs, and you obtain an automatic selection of the relevant term. But that's a tricky question, to be able to select just the right ones.
I think it's an advantage of Gaussian processes that, yeah, if you know something about your physical process, so if you know it's got these long-term trends and these short-term trends, you actually know a lot about what you're saying when you put the length scales in. So very often you have this domain knowledge about the problem, and it's quite easy to include the domain knowledge in the right way by initializing your kernel. It's not that you can't find the truth, it's just helpful to initialize the model somewhere close to the solution. And the parameters are very, very interpretable. Now, if you look at other data-driven techniques, such as in the old days we always used to use like neural networks for this type of problem, it's really difficult to sort of say in a neural network type setup, which is a sort of adaptive basis function model, I've got two length scales in this process and I want to search for them both, because it's difficult to specify in the model. The meaning of the parameters of the model is much less clear. Whereas in the Gaussian process, you're right, to find this example, you would have to know that you were two length scales and include a kernel, or search across kernels. But it's become an optimization problem about something you're interested in, and when you get the answer, you know what the answer means. So if the model comes back and says, yep, there are two length scales, and overall, it will give you, like, these variances are really interpretable in this case. So if it says that sigma squared 1 is 1.2 and sigma squared 2 is 0.2, you know that the variance of the small length scale is approximately 20% of the variance of the long length scale, and then you get a noise parameter as well, which is giving you the signal to noise ratio. Overall, you can compute the signal to noise ratio and everything like that, whereas that type of information doesn't come out of a less interpretable model. So I think your point's correct that you might have, in order to extract this, you might have to have a bit more domain knowledge, but the framework you have actually allows you to incorporate this domain knowledge in the correct way, whereas most frameworks you'd be stuck with, well, I think that's what's going on, but now what do I do about it? Yeah. So you painted a very nice picture, but I want to push you on some sort of things we can't design kernels for. So what about positive constrained functions?
Yeah, that's a good question. When I was talking at the end of my talk about making this kind of applications that were able to project a function into somewhere where into a subspace that shares the informations we have. So Neil's question was about, okay, I know that my function is positive, and if I sample draw from my Gaussian, a usual one, I will end up with some negative values. And is there a way to constrain the GP to be greater or equal than 0? So one option would be to start to look for this kind of operator to be able to take a function and to project it onto the subspace we are looking at. But if you pay attention, the very first condition we have for these to work is that the operator L has to be linear. And there is no linear operator in the sense that L of f plus g equal plus L of g. You will not find a way, you will not find an operator L that will project functions just onto the positive half of the plan, onto the upper half of the plan, that will share this linearity. So this framework here cannot be applied. And the other thing you can see is that if you're looking for a distribution of function that has a probability equal to 0 in all this region, then you can't look over there for a Gaussian distribution, because a Gaussian distribution will always have some weight in this region. So that's two arguments to say that Gaussian processes are not well suited for this kind of condition, and then you have to start thinking about non-Gaussian likelihood to reflect this knowledge, and that's because this kind of knowledge cannot be seen as a linear application applied to a function.
Other questions? I might ask a silly question.
Yeah.
So you can use the sum of two kernels or product of two kernels.
Yeah.
So in what case do you use which one?
I would use the sum of two kernels if I want either to approximate a function that has quite a large additive component, so not purely additive, but if it has a global additive behavior, I would take a sum of kernel plus some noise or plus a product to take into account these variations. Or I will use the sum of kernel if I'm in very high dimension and I have a few points. I would say, okay, so I will just use a sum of kernel because with the knowledge that is given by my point, I can't expect to have much more information that what is the additive component of this function. So it's kind of a trade-off between the number of points you have and the dimension you have. And yeah, in a sense, if you take a problem with an increasing dimension, if your number of observation is growing in a linear fashion, there's no way to have good results with a product kernel, whereas an additive kernel will not approximate the function very well if the function is not additive, but it will be able to extract the information, so that's what you can do with your budgets. Yeah?
I mean, another way of thinking about that is to draw what Nicolas has done with the draw these kernels. So if you're adding two kernels together, so you're adding the two length scales, this is the, I don't know how to pronounce that, my lower example, you get one thing like that and one thing like this. So you get a covariance function that looks sort of summed together, the sum of these two things. But if you do multiplication, so almost like either of these things is allowed to be true in the kernel, but if you do multiplication of these things together, so if you combine, I don't know, what two could you combine? When you multiply two together, for example, if the function's correlated under one but not under another, it will just squash everything out. So basically you lose the correlation. So if you're thinking in the elements of your covariance, k1 dot times in terms of element by element multiplication times k2, in order for this to have a non-zero entry, it must be non-zero in both cases, right? So if either of these kernels on its own says these are uncorrelated, then the combination will say uncorrelated. But if you add them, then even there's a zero in some place here, there could be a non-zero here, so you can still obtain the correlation. So you can get these effects if you want to sort of have, like, it's almost like you want both of these kernels to agree that something's definitely correlated, you take the product. But if you sort of don't mind that either can say something's correlated and it comes through, then you want this sort of structure. And it can vary according to circumstance. Yeah. Other questions?
I make this one thing. Apologies if it was what I wanted, but once you make some choice, how do you know if it's a good one or not?
I'm sorry?
Once you've made some choice about your kernel, how do you judge whether it's a good kernel?
The thing I would do is to take some new points and evaluate my model and look at if the distribution I obtain for my error is in the law that is given by my model. If I don't have budget for more points, I will do something one out, or You can leave many out and look at if the joint distribution is the one that is predicted by your model. But yeah, that's the way I...
Just all out to sample prediction.
Yes, yeah, that's the way I would go. Nothing, I don't know anything fancy for it.
I mean, we talked about kernel parameter fitting this morning, and you can use those sort of techniques to show that your one kernel's higher likelihood than another.
Right.
That doesn't give you any guarantee. It's picking me up from here anyway. That doesn't give me any guarantee that it's the right kernel, though. And that's one thing we always have to be careful about with the Bayesian inference arguments from earlier. All you can ever say with these sort of Bayesian inference arguments, comparing model evidence, is that one is better than the other. It doesn't mean it's correct or it's the best possible model. It just means given two models, it prefers one model over another. So we can use those sort of approaches also to estimate, but I think it's sensible, as Nicolas says, to always have sanity checks by, once you've estimated everything, doing some leave one out or cross-validation of some kind to ensure you're predicting well in domains where you're missing data.
Your zero mean kernel, in which way can you, so in which domain is it zero mean? I don't quite got how you say zero mean.
Here I just consider a compact domain.
Okay.
So say, yeah, a real interval. You
And
can have it in
define-
higher dimension if you want to, but I'm not looking at zero mean kernels over R.
Okay.
Because then it becomes a bit...
So you have your observations and say it should be zero mean from observation 0 to observation.
Yeah, I specify a range.
Okay.
And so,
I assume my input spaces now. But you can... Actually, you don't... Yeah, I said that I specify a range because the measure I was using here is the uniform measure, which is kind of an improper measure of R. But I have some other examples where I'm doing that over R, but I assume that my points are Gaussian distributed, so I'm working over R, but my integration measure is the Gaussian. And then you can end up with exactly
yeah.
the same results, but yeah, where these integrals here I took uniforms, so I specify a range, but okay, you have exactly the same results over R if you have a proper distribution for a proper measure to integrate with.
Oh yeah.
I think, I mean, also it's worth, Jeremy's done work on elicitation of priors that use this trick to, I think you use a Gaussian measure for the integration, don't you, with the prior elicitation work? So you multiply it by a Gaussian and then constrain the observation of the integral to be 1 across the real line. So the problem, so in that work, what and Jeremy can step in if I'm mischaracterizing it. What you're trying to do is create a Gaussian process approximation to a probability distribution. So you know they integrate to 1, so you can include this information that it integrates to 1 when building your kernel. But the domain question that Max was talking about means that you want it to be across the entire real line that you integrate to 1. So they build a special, they basically construct that under a Gaussian density. But then you do end up with the problem that you can't constrain it to be a positive function in practice, and probability densities have to be positive functions. So I think you rely on the data to force it to be positive.
I think someone wants to try. I think there's a way of conditioning on it being positive at particular points. So if it's causing problems when you're simulating realizations, you kind of nail it to be non-zero, to be non-negative at points where it's causing difficulty, and that helps. But in practice, it wasn't. We didn't have a problem getting positive realizations where we wanted.
Yeah. So, and that I think will relate to also work that will be talked about on Wednesday, where I think Mike Osborne and or Philip Hennick will probably talk about work that's also coming from the stats department here, and they're looking at extending ideas of Bayesian quadrature, where you're using Gaussian processes to estimate these Monte Carlo integrals, and you end up with the same problem there. You try to fit a Gaussian process to some function you want to integrate. You know it's positive, and I think some unusual things can happen. But Mike Osborne may mention things about that on Wednesday. Other questions? Great. So we're on time, 5 minutes early even.
Yeah.
So if we just thank Nicolas again. And I think we start again tomorrow at 9. Are there any organisational announcements?
There's a pub just nearby. So
Organisationally, yeah, there's you actually you can get to it two ways, either along the road or you can go out down this staircase you see down there, and then there's a pathway up to the behind of the pub through a little forested glade there, which is the way I like to access the pub. So you can walk down if you're interested in having a sort of some liquid refreshment in order to help discuss Gaussian processes a bit more, or anything you like. I'm sure some people will be doing that, and it's called the Francis Newton. Yeah. Okay. Great. Thanks very much.